In this segment, we'll take an example of to see that if somebody is asking us to solve a set of simultaneous linear equations, how can we figure out how many significant digits we can trust in our solution. So let's suppose somebody gives you a set of equations which looks like this: 1, 2, 2, 3, unknown vector xy is equal to 4, 7. And so somebody is giving you that as a problem statement. Somebody is giving you this set of equations saying, hey, can you tell me how many significant digits I can trust in my solution? So in this case, what I'm going to do is I'm going to say norm of A times norm of x is equal to c. So that is the form of this set of equations. This is the coefficient matrix, this is the unknown vector, and this is the right hand side vector. And I want to find norm of A. And norm of A in this case will be 5, because the addition of these two elements, the absolute value addition of these two elements is absolute value of 1 plus absolute value of 2 is 3. Absolute value of 2 plus absolute value of 3 is 5. So the row sum norm is 5. And then we're going to find the inverse. So what we'll do is I'll give you the inverse of the matrix. There are several different ways of finding the inverse of a matrix. So the inverse of this matrix is -3, 2, 2, -1. That's what we get. So in this case, norm of A inverse will be also 5 based on the infinite norm or the row sum norm, because absolute value of -3 plus absolute value of 2 is 5. Absolute value of 2 plus absolute value of -1 is 3. So the maximum of those is 5. So that's why the inverse of the norm of the inverse of A is 5. So what that gives us is that the condition number of A will be norm of A times norm of A inverse. And if that's the case, then norm of A is 5, norm of A inverse is also 5, that gives us 25. So now what I'm going to do is I'm going to compare this with, I'm going to find this number, condition number of A times the machine epsilon. So the machine epsilon can be corresponding to whatever precision of the precision we're using, whether we're using single precision, double precision, or quad precision. So let's suppose we are using single precision. Then in this case it will be 25 times 0.119 times 10 to the power -6. So that is the machine epsilon for single precision real number. And then in this case it turns out to be equal to 0.2980 times 10 to the power -5. So then what we have to do is we have to see whether this number right here, how does that compare with how does this number, which we get as the product of condition number and machine epsilon, how does that compare with this 0.5 times 10 to the power -m. So we're looking for the largest value of m, integer value of m, positive integer value of m, for which this inequality is true, and this turns out to be m is equal to 5. Of course, this means m is less than or equal to 5. That's what you will get when you solve this inequality. But we're looking for the largest value of m for which this inequality is valid. That when is the condition number times the machine epsilon, which is the measure of the relative change in the solution vector to the relative change in the right-hand side vector or the coefficient matrix. This is what we get as condition number times machine epsilon, and we compare it with this number, we get m is less than or equal to 5. So 5 significant digits can be trusted in our solution when we are working on a single precision machine for this case. If we're going to use double precision or quad precision, surely this number will increase accordingly. And that's the end of this segment.